This is our third and last video that involves section 1.3. We're going to finish up the lecture portion with this one by introducing one more word, more vocabulary of linear algebra. And the word we're introducing here is span, the span of a set of vectors. So first, let me give you a definition, then we'll look at a couple examples. Let v1, v2 through vn be a set of vectors, all of the same dimension. So they're all, 2 entry, 3 entry, 4 entry. They all have to have the same number of entries. The set of all possible linear combinations of v1, v2 through vn is called the span of v1, v2 through vn. All possible linear combinations, so just not one particular one or 2 or 3, but every possible linear combination you can get by taking real number weights times each vector separately and then adding that together. The notation that we use in our textbook for this is span, then set notation of the vectors, up here the vectors involve v1, v2 through vn. Now let's look at a couple examples that I hope will bring this to life a little bit for you. Nice visualization, nice geometric situations. So we're in R2, so we're just looking in the plane, and we want to talk about what's the span of the vector 1, 1 and 2, 1. I'm going to use arrows to help me visualize here. So 1, 1 be a vector like that. 2, 1, so over 2, up 1 would actually be a vector like that. So there are my two vectors involved. Now I can maybe give these names. Maybe let's call them v1, v2. So how can I get linear combinations? Well, there are a lot of things I could do. I could take v1 plus v2. That's sort of like 1v1 plus 1v2. And that's going to be 3, 2, right? So 3, 2. And what I should be able to do here, I should be able to complete my parallelogram and get the sum of those two, right? Either represented by this point, or I could draw another arrow. If I took 2v1 plus v2, okay, I would take 2 of the first plus the second, and I get another vector here. I could take v1 plus 2v2. I mean, this goes on and on forever. If I take 2v2 plus v1, and what I'm trying to draw here is sort of a diamond tiling of the plane. In fact, out here, I think this is what I would get if I took 2v1 plus 2v2. If I took negative multiples of either one, if I took negative v1 plus v2, let's see, negative v1 would point this way, plus v2, negative v1 plus v2, I think going to be approximately there. Again, my drawing is a little wiggly. And I could take negative multiples of both and add those together. And what I want you to think about is I could create this sort of diamond-shaped checkerboard covering the entire plane by taking a multiple of one plus a multiple of the other. But now I really get a lot more than that. Try to fill this in a bit with some more of these possibilities. Because it's not just integers that I can use as weights. I could take, for instance, 1/2 v1 plus 1/2 v2, or different numbers, 1/2 v1 plus 1/2 v2 is actually going to give me a point kind of right at half of one of these, half of one of those inside. In fact, by using fractions, I can get every point inside that first parallelogram filled in. And then by using like 1.5 or 1.5 or 2.5, I can fill in all these other points with, I can get sums that add up to points there. So I'm trying to convince you that we can actually cover the entire plane R2. We can get any vector at all. Now I could just pick one at random and try to get that, but even that vector can be described as a linear combination of v1 and v2. But we don't have to go back and solve here. I just want you to make this observation that by writing down so many different possibilities, we can see that we're going to cover the whole plane R2. And so the span of 1, 1 and 2, 1 is R2. Now, I haven't proven that mathematically, but really my point here was just to kind of get you to think conceptually about what all the possibilities are. And 1.5 v1 minus 3.5 v2, etc., we will get every single possible vector in R2 out of that. The span is equal to R2. Okay, now one more example. Looks kind of similar, right? Here's the span of two-dimensional vectors. 2, 1 again. Okay, there's our 2, 1. But this time it's 4, 2. So I want to try to draw it here. 4, 2. 4, 2 is actually going to lie on this. The arrow for 4, 2 is going to lie on the same line as the arrow for 2, 1. If this is our v1, this is our v2. Just notice that v2 is actually equal to 2 times v1, and I chose them that way on purpose. One is a scalar multiple of the other. And so in the plane, visually, that means, again, one is twice as long as the other on the lying on the same line. Now, if I start taking linear combinations of v1 and v2 here, like v1 plus v2, or 5v1 plus 3v2, can you see that whatever I do, I'm always just going to get vectors on this line? I can't get off the line. I can take negative v1 plus 0 v2, which would just point that way, right? Or I could take negative multiples, negative v1 minus 5 v2 of both. So negative numbers will just take me in the opposite direction. Fractions, 1/2 v1 plus 3/2 v2, are not going to take me off this line. So the span of these two vectors is very different from the span up here, where we can get every single vector in R2 from the span of these two. The span of these two and is limited, right? And it is because they were related to begin with, right? Is equal to a line of vectors in R2. So it's not all of R2. And if you wanted to describe all these, they're all scalar multiples of 2, 1. So if we wanted to be a little fancier in our answer, we could say it's the set of k times 2, 1 such that k is any real number. It's really all all scalar multiples of, I could have picked either one of these, doesn't matter which one I pick. But for homework purposes there, test purposes, I would have been perfectly happy with this answer because this is more conceptual than a calculation. We get a line of vectors here for the span of those two, while we got the entire plane. Every single vector in the plane is in the span of these two. So that's it. Next video lecture next will be on section 1.4.